Now it turns out, based on what we already know, we actually can't solve this problem. We need a new mathematical technique. So let's go into what that new mathematical technique is, and that is the technique of Green's functions. Okay. You would have heard the name of Green in the context of vector calculus. Some identities of vector calculus are named after Green, right. So he worked a lot in this area, so things go after his name, right. So lot of material here, let's go one by one. I have these two equations. The entire current source part has been condensed into one term Q. Okay, this is physical constants multiplied by the current. So, I am going to call it Q. Now, as I said, these two equations are not sufficient to solve this problem. So, now I am going to seemingly make life more complicated before making it simple again, right. So, what is the new complication? I have introduced two new functions. I am calling them G1, G2, and what are their properties? They satisfy these two equations. So, let us just read out the first equation. So, it says del squared G1 plus K1 squared G1 is the negative of a delta function. Okay. So, this delta function is your usual Dirac delta function, right. So, we all know what is the property of a Dirac delta function. It is 0 everywhere and infinity at the point at r is equal to r prime, and it is not actually a proper function, right. So, but I can talk about its integral. The integral of a delta function, as long as I cover this point of singularity, is 1, right. So, what I have done is I have introduced these two new functions. Also, because we are going to write r and r prime again and again and again, I have dropped the vector sign over r. Okay. So, even though I have written just r, it is understood that when you see r, it is actually r with a vector on top, but it makes the whole thing very clumsy. So, I have just removed the vector sign. Okay. So, it should be clear to you from the context when I am referring to the vector and when I am referring to the absolute value of r. Okay. So, before we get into anything, does this equation remind, what are the similarities between these two equations? Are there any similarities? Looks the same, right. So, the both of these equations look like this: del squared something plus k squared something is equal to something. That seems to be the general template into which these two equations are fitting, right. If I make the right hand side non-zero, I get the second equation. The other, if I ask you what is the difference, the first equation is an equation in only one variable, r. The second equation, now I have introduced one more variable, r prime, okay, which will seem a little strange at first, but we will see, it will make life very powerful. Finally, this del squared operator, this is acting only on unprimed coordinates. Okay. So, when it encounters any function of r prime, it is a constant, right. So, this we will say only acts on unprimed. Okay. That is fine. So, that is just an assumption. So, I need not actually write it over here. Okay. Okay. So, now how do we actually proceed with this? So, well, the trick that we will do is, we will take the first equation. Supposing I take this first equation, multiply it by G1, take the second equation, multiply it by phi 1, okay, and subtract these two. By subtracting these two, is there any advantage that I get? The right hand side? Not the right hand side, nothing much will happen to it. On the left hand side, how many terms are there? There should be 4 terms, but as a result of multiplying this by G1 and that by phi 1, what will happen? What will happen to the k squared terms? They cancel off, right. So, I will have a G1 del squared phi 1, okay, minus phi 1 del squared G1, right. K square term goes away, and now I am left with the right hand side. So, the right hand side was, or rather is, q, okay, plus phi 1 delta r minus r prime. Okay. I am being a little sloppy here. You know that all of these guys g1, phi 1, all of these guys are actually functions of r and r prime. Okay. Okay, so what will the k1? So I will have a k1 squared phi 1 multiplied by g1 from the first term, and from the second term I am subtracting them. So I will have a k squared, k1 squared g1 multiplied by phi 1. I am subtracting these two equations, right. So this gets cancelled. So I am just left with this. Okay. All right. So still looking at this, it seems even more confusing than when we first started out, right. But it's a few steps that we have to take. All we managed to do is get rid of this k squared phi term. Okay. We still need to do a little bit more vector calculus. So here is the identity for what do we call this? The product rule in vector calculus. So I have two functions g and grad phi. So when I want to take the derivative of the product, in vector calculus it becomes divergence, right. So before we get into anything, look at the left hand side. Is the left hand side a scalar or a vector? Grad g is a vector, g is a scalar. So this is overall a vector, and when I take the divergence of a vector, I get a scalar, right. Look at this term, this is a vector, this is a vector, dot product scalar, del squared of a scalar is a scalar multiplied by g, right. So at least dimensionally it makes sense. I am not writing scalar equal to vector. So this kind of basic check you should do when you write down this expression. Okay. So using this identity, can I rewrite the left hand side of this equation, right. So if you look at this one, if I try to write down g1 del squared phi 1 minus phi 1 del squared g1, I can write that as equal to, what will I write it? Del dot g1 grad phi 1 correct, because again del dot g dot del phi will come both times, it cancels off. Okay. All right. So this is one manipulation that we did. So we will keep this result with us, we will hold it in memory. Now so far, we started by saying that we are going to talk about integral equations, but so far there is no integral anywhere in sight, right. So to introduce that integral, what we need to do is, let us take this equation that I have and let us integrate it over a volume V. Let us integrate over volume V1. Okay. So this whole thing dV over V1, that is what we are going to do. Okay. Do any of the terms, do you see them simplifying? Yes, V1 is the region of, is the volume of region 1. Okay. So the only possible term that might simplify in this volume integration is which one? What about the very last term? I am integrating over a delta function. That is the only term that seems to be that, okay, it might simplify. Okay. The other terms, it is not very clear how they will get simplified. Okay. So let's see how they will. Del squared?
You can write it as some curl.
Yeah, okay, you're getting to what I am getting to next. You notice that when I integrate this term over here over volume, this becomes an integral of this over volume, right. So that is what we are coming to. When I have, so what was the divergence theorem in 3D? It said that when I integrate del dot A over dV, I got the flux of A over ds. That was in 3D. We are used to thinking of divergence theorem for all the years of our schooling. We are used to thinking of it as a 3D thing, right? There is a volume and there is a surface flux from it. But actually, there is nothing preventing you from formulating this theorem in higher or lower dimensions. Okay? The main idea is that if I have a volume in n dimensions on the left hand side, I have the corresponding surface in n minus 1 dimensions on the right hand side. Okay? So, since our problem is actually 2D, not 3D, the divergence theorem gets simplified in 2D as follows. So, I have to drop one dimension. So, this volume, this was a closed volume and a finite volume, right. So, this will become a finite surface, right, and dV will become ds, ds will become dl, okay. And remember, this ds was nothing but n hat ds, like this, right. So, this is your divergence theorem in 2D, right, and if you want to think of it as a surface, it is like this, some surface, the left hand side is being evaluated inside and the right hand side is being evaluated on the boundary, okay. It is a contour integral.
The DL n cap should not be there, no? N cap is a normal.
N cap is the normal, so it is the outward, yeah. So, dl is this, it is the flux through, dl in the normal direction. Over here, wasn't that the same interpretation? It is the flux of A along n hat in a small area patch. That area has now become length element, right. So, it is a one-to-one mapping of this divergence theorem to 2D, okay. And this is again very simple. If you just use the definition of divergence and all, you will get this, if you wanted to derive it, okay. Okay. So, we need to now apply this divergence theorem to region 1 over here. Okay. So, our region 1, just one sec, okay. So, let us see. So, this is our region 1, okay. I am trying to draw region 1 over here. This is my V1, right, region 1. What are the two boundaries of this? I have S and S infinity, okay, and I have drawn the normal vector like this. Actually, if I think of these as finite surfaces, if I think of S infinity as a finite volume, then when I apply the divergence theorem to this volume over here, how many surface integrals will I have to take care of? In this case, the volume was enclosed by one surface, and so I had to take care of the flux through that surface, right. So, this was very straightforward. In this case, if I apply divergence theorem to this volume, I should take care of the flux that is leaving the volume, right. That is the conceptual meaning of divergence theorem. Divergence of sources inside is equal to outgoing flux. Now, in this case, this volume 1 is bounded by how many surfaces? Two surfaces. Flux could be leaking through S outwards or through S infinity outwards. Okay. So, when I write down this divergence theorem, I have to write down the flux through both surfaces, right. So, let us call the opposite of this vector over here, right, that is the outward normal over here, let us call it n1, okay, and let us call this n infinity. Okay. So, the divergence theorem applied over here will give me what? Del dot f ds will give me the total flux. So, it will give me over S as f dot the outward vector, outward normal to this, which is n or n1? N1, right, it is the outward normal, because I am looking at all the flux that is leaving this volume. Okay. So, this is N1, okay, outward flux, plus f dot n infinity dl, just straightforward budgeting of the fluxes, right. Now, as S infinity is actually it is far away and our source is fixed over here. So, what do we physically expect to happen on the boundary S infinity? Fields should go to 0, right. So, this term is going to go to 0. Okay. Coming to the second term over here, what will I write it as? Second term survives as is. Okay. N1 and N, what is the relation? They are just opposites of each other. So, I can write this as okay, and only reason is because I had earlier decided to call the normal to this surface as this normal going outwards in this direction. But when I am doing the divergence theorem to volume 1, you notice that I have to take the correct outgoing flux vector, right. So, I could solve the whole problem with N1 or I could solve it with N, convention, depends on me. Okay. I am going to choose N. So, N is the inward normal, that is why there is a minus sign.
So when we define n hat, it's as a function of r.
Yeah, as a function of where the boundary is.
Yeah. So I mean everything you have to you finally have to write everything in r.
Yes.
So at the positions of the boundary it has some value.
Yeah.
And others 0.
Yeah, so n hat, so this remember this integral is a contour integral, it is evaluated only on the boundary, it is not evaluated in a volume, right. So, it comes into picture only on the boundary where a normal has been defined. Okay. So, we will make use of this. Going back to what the vector calculus identity we had on the previous page was this guy, right, and we had integrated over volume, there is a dV missing over here, right, and in this case it is ds because I have moved it down to a 2D problem. Okay. Using what we had derived earlier, this became del dot this whole thing, and del dot this whole thing becomes what? Here is where we apply our divergence theorem, right, and so this will become negative over S g grad phi minus phi grad g, okay, dot n hat dl, okay, and this is over V1. That fine? So, nothing very complicated. We basically we started with our two equations over here, these two guys, subtracted it with these two Green's functions. Okay. I have not told you anything about these Green's function. So, we are just assuming that we know them. Okay. In another module, we will talk about how to derive them, but for now let us assume that they are known. Okay. We subtracted them and applied some vector calculus to get this relation, after which we applied our divergence theorem to get this relation, right. Okay. Now, if I go back to this equation, this also was going to get integrated with respect to volume, right. So, this was a G1 R R prime Q R dV over V1, right, that was what the volume integration was. Okay. So, if I do all this integration, these are all known things. Okay. I have not told you how to calculate G, but we will get to it. So, G1 is known, Q is been given to you in the problem, because Q is capturing what? The current source. So, this term is given to you. Okay. So, this is known to me, I am going to call this it is like the incident field, because it has information about the current source. What comes out from a current source? Some incident field which is going to get scattered, right. So, I am going to call this phi I. What should it be a function of? R or R prime? R prime, right, because I am integrating over the place where the current source and all is, current source is a function of R, right. So, I am going to be left with R prime, okay, and that is thanks to this guy, because G1 is a function of R and R prime. If G1 were a function of R only, then it would just be a number, this integral, okay, right. So, now we are going to put all of these chunks together, okay. This is the term that we have to keep a bit of an eye on, right, because all other terms you have simplified. So, phi I became that current term, okay. This minus this term over here has appeared over here, okay. What is left was this final term over here, right. So, that is phi 1 of r delta of r minus r prime dv integral over v 1. So, what will the value of this function be? I have a delta function, it is multiplying by another function and I am integrating. So, phi 1 r prime, right, that is almost correct. So, look what is happening over here, right. So, this is, let us say I have one point over here r, I have one point over here r prime. Okay. So, if the volume of integration, if it, it will only induce, well, not one, but so this is this Dirac delta function is a function in those many dimensions. So, if it is a volume integration, it is a 3-dimensional Dirac delta function. It is a 2D case, so it is a 2-dimensional Dirac delta function. So, wherever the singularity is, that is wherever r is equal to r prime, if it is there, then this delta function will extract the value of the function inside the sign, right, except two conditions are there. When I say, what I am doing is I am integrating over this region volume 1, that is what I am doing, not the entire space, right. So, have I said anything about the location of r prime? I have said absolutely nothing, right. When I introduce r prime in this equation, I did not say a word about where r prime is, it just came as some variable, right. So, when I look at this volume over here, I have not told you where r prime is. R prime could either be in V1 or it could be where? V2. If r prime is in V1, that means r prime is, let us say, here, and I am integrating over that volume which contains r prime. That means there will be one point where r is equal to r prime, and when I integrate the delta function over that volume, what will happen to this integral? I will get phi 1 of r prime, exactly. On the other hand, if r prime were inside here and I am integrating over V1, what will happen? What is the value of the delta function? Is 0 everywhere, right. So, you can see how Maxwell's equations and vector calculus, they sort of going like a dance almost, helping each other along the way. We have come to this final equation over here, right, and in the subsequent slides we will give a very beautiful physical interpretation to it. Okay. So, we will talk about that subsequently. The top equations, there are actually two equations over here. One is when r belongs to r prime belongs to V1, and the second is r prime belongs to V2. So, when r prime belongs to V1, you do not recognize it yet, but this is actually nothing but Huygens principle. Okay, and we'll give a physical interpretation to every term. This thing is something that you have not encountered so far or even heard the name of, but this is called the extinction theorem. Okay. So, one good question is that why can't we think of solving these equations by themselves, right. In the previous problem where we had the line charge, we just took them, discretized phi 1, integrated and got the solution. The trouble over here is that Maxwell's equations you also have to impose boundary conditions, right, because you have two different volumes, right. So, what is to be respected on the boundaries? Tangential E field, tangential H field has to be conserved. When I look at just these two equations over here, these two equations, there is no mention of boundary conditions, right. This is a point by point relation over here, and there is no way for me to impose the boundary condition. As two different variables.
They don't mean anything mathematically.
Well, mathematically they are the electric fields.
But they don't have the volume differences.
Yeah, they don't know which is volume 1, which is volume 2, right. So, that imposing the boundary conditions is not possible purely with this. In the other problem, there was no boundary really, right. The charges are there on the surface and that is it, right. Here, that is why I am subtracting these equations and then integrating over one particular volume. So, we integrated only on V1, then we will integrate only on V2, and you can see that this equation that I have, right, this is actually now operating only on the surface. This right hand side over here is going to be the way I am going to impose the boundary condition. That is where, so that volume has been converted to a surface and boundary condition will get applied on the right hand side over here. Okay. So, that is why we do this trick of integrating over volume then using divergence theorem. Okay. Good question. Alright. So, with that we will bring this discussion to an end, and subsequently we will look at the physical interpretation of these terms.